Okay, as you know, we'll learn physical fundamentals of multimedia systems. The most important that we will learn is some physical laws. They may be important for you if you will work, for example, in game development, or if you will develop some software for different devices. In all these areas, physics may be useful. And first part of physics that we will learn is mechanics. And the first part of mechanics is kinematics. In kinematics, we will learn motion without different factors that can affect on motion. So kinematics is something like geometry in which objects may change their place in space. So it is something like a mixture with geometry and motion. This is kinematics. And main objects in kinematics is a material point, a perfectly rigid body, solid media, and perfect liquid. And first of all, we have to study material point because all mechanical systems may be described as systems of material points. And so what is material point? Material point is body which dimensions may be neglected according to a problem that we consider. And for describing of motion of material point, we have to set reference system. We have to set reference system. And what is a reference system? Reference system is a connection of initial point and Cartesian coordinates. So I will draw this. I think in most general case, it will be 3 dimensions. 3 dimensions are necessary to define place of material point in space. X, Y, Z. X, Y, Z are Cartesian coordinates. And initial point is O. Here we can define place of material point M by setting its coordinates X, Y, Z. 3 numbers X, Y, Z. It may be real numbers. 3 real numbers X, Y, Z are enough to set place of material point in 3-dimensional space. But these coordinates are not only one way to define place of material point. It also may be defined by radius vector. What is radius vector? It is a vector that's initial point is in origin, and final point is in place of material point M. So on this picture, radius vector is something like this. Radius vector is vector that has initial point in origin, and origin is here. And the final point of radius vector is in place where material point presence. So it's something like this. And how to connect? How to connect coordinates x, y, z and radius vector. Radius vector. In fact, they are equivalent. These ways of defining place of material point are equivalent. But to connect them, we have to define orths of coordinate axis. Orths are vectors that have lengths equal to 1, and they can be signed as I, J, K. As you can see, they have directions that are the same as directions of coordinate axis, and their lengths are equal to 1. So we can write that absolute value, what is the same as length of vector, absolute value of E is equal to absolute value of J is equal to absolute value K, and this is equal to 1. So EJK are orths of coordinate axis, and if we define them, we can connect radius vector and Cartesian coordinates of material point M. So we can write R is equal to xi plus y j and plus z and k, plus z and k. And sometimes it is necessary to know absolute value or modulus or length of radius vector. It can be defined by Pythagoras theorem. In this way. R without line above it, it is equal to absolute value, and it is equal to square root of squared x plus squared y and plus squared z. In this way. Okay, do you have any questions about this?
So far, so good. Everything is clear right now.
Okay, and where can you meet Cartesian coordinates? For example, to define a position of pixel on the screen, of pixel on the screen, Cartesian coordinates are used. But the origin of these coordinates in left upper corner of the screen. So in this case, we have Cartesian coordinates of two-dimensional space with origin in the left upper corner, and this is y, and here we have x. But coordinates of pixel on the screen may only be integer. So it is they are not real numbers. They are always integer numbers, and sometimes this is necessary to take into account when you define place of pixel on the screen. So okay, if we understand this, it is necessary to say that coordinates of material point may change in time, because we are learning motion. Motion means that x, y, z change in time. So they are functions of time. So we can write that x is a function of time t. This means x is a function of time t, and in the same way, y is a function of time t, and z is function of time t. And in the same way, we can write a radius vector. Radius vector is a vector function of time. And of course, it can be written. As x as function of time, e plus y as function of time t, j, and plus z as function of time t and k. T. So these are kinematics equations of motion. I think I will write this. So these are kinematic equations of motion. If you know this equation, we can define place of material point in each time moment. So these equations are enough to define the place of material point in every time, or at any time. So kinematic equations of motion. And sometimes it is necessary to define trajectory of material point. As you know, if we have material point in motion, it always moves along some geometric line. And this geometric line is known as trajectory. And this trajectory can be described mathematically with trajectory and equation. Trajectory equation can be uh, got from here, from kinematics equation. And to do this, to get trajectory equation, we have to exclude time. We have to exclude time from kinematic equations of motion. And if we do this, we will get trajectory equation. And what else it is necessary to say? As you know, motion may be slow or fast. So material point may change its position in slow way or in fast way. So we have to describe mathematically what means slow and what means fast. So to do this, let's draw another picture. I will draw two-dimensional picture, but in a general case, situation will be the same. So we have two-dimensional Cartesian system x, y. Origin is O, and let's draw some trajectory of material point motion. It will look like this, and let's draw initial position with let's define initial position with radius vector r1. R1 is initial position m1, and final position is r2. R2 is a final position of material point. Final position we will assign as m2. And in this case, material point passes path from m1 to m2, and this path length is length of this part of trajectory, and the path length is equal to some delta s. Delta s is path length. So length of this part of trajectory between m1 and m2. This is delta s. And we can also define so-called displacement vector. What is displacement vector? This vector has begins in initial point and ends in final point. Displacement vector. On this picture, it will be here. Delta R is displacement vector delta r. We can write displacement vector it is equal to, according to the picture, delta r is equal to radius vector r2 minus radius vector r1. Or it can be written in some another way. It can be written as r at some time moment t plus delta t. Delta t is some increase of time, and the minus r in some time moment t. So this is displacement vector. And as you can see from picture, the absolute value or length of displacement vector is always less or equal than path length. Is always less or equal. And equality will be in only one case, in only case of rectilinear motion. Rectilinear motion is a motion along a straight line. If you have motion along the straight line, there will be equality. And we can also notice that if we take shorter displacement vector, its length will be closer to path length. So if we consider infinitely small time, we will have something like, we will have formula dr is the same as d absolute value of infinitely small displacement vector. This is the same as limit when increase of time tends to zero, absolute value of delta r. Absolute value of delta r is length of displacement vector, and this is the same as limit delta t tends to zero, delta s, and this is the same as ds. And what is necessary to say? It is necessary to say that we have to consider ds and dr. So ds is one symbol, and dr is also one symbol. So it doesn't mean some d multiplied by r. It is one symbol, something like one variable in programming, dr ds. And this formula, I think it was strictly proven in calculus, or what is the same, mathematical analysis. Now we just need this. We just need this to move forward in our studying. So I will frame this in blue rectangular because we will need this in future. We will need this in future. Okay, do you have any questions about this?
I think so far so good, I think. Yeah.
Okay, so if we have displacement vector, and as I have already said that displacement may occur in along long and short time, so we can define velocity. So average displacement velocity is displacement vector divided by increase of time. So let's define average displacement velocity. Average velocity of displacement. Average displacement velocity. Average displacement velocity is equal. It is equal to. It may be written in some angular brackets or elevator brackets. Is average velocity, and it is equal to increase of radius vector t plus delta t minus r at time t divided by increase of time. And this is the same as delta r, increase of radius vector, or displacement vector divided by increase of time. So this is average displacement velocity. So all displacement vector divided by time. So it's quite simple definition. But this definition is not enough to describe motion. Why? Because if we imagine, for example, motion of car, we can remember that initially velocity of car increases, then it may be constant, or or not. So velocity of car may change, and then before stop, velocity of car becomes slowly, and then car stops. So we have to define velocity more carefully to better description of motion. And we can notice that the less increase of time we have, the better description of velocity we will get. So to get more accuracy, to get better accuracy, we have to take less increase of time, and in and to get the best accuracy, we have to take infinitely small increase of time. We have to take infinitely small increase of time. So we can define instantaneous speed. Instantaneous speed. Instantaneous speed, or in practice we say only speed without word instantaneous. So it can be defined as v vector. Vector v is limit increase of time tends to zero. Here we have average displacement velocity, and here it will be a limit delta t increase of time tends to zero, and here increase of radius vector t plus delta t minus r in time t divided by increase of time, and as you can remember from your calculus course, it is here we have definition of derivative. So it is derivative of radius vector, which can be written as this fracture. So we have that speed is equal to derivative of radius vector, and this can be written in some another way. If we use these equations of motion, so we can use this here. Dt It means derivative. And now I think I will copy this string. I will copy this string into brackets to make substitution. And if we calculate this derivative, we can see that here we have linear combination of three functions, x, y, and z. They are functions of time, and orders of orders e, j, k are constants. So we can write that it is equal to Vx e plus Vy j and plus Vz and k. Vz and k. So in this way. And what is Vx, Vy, and Vz? They are derivatives of coordinates. So Vx is equal to derivative dx by dt, and in the same way we define other two derivatives. We define the other derivatives as defined by this formula y and z. Y and z. Okay, do you have any questions about this?
Nope, I'm okay.
Okay, thank you. That's great. That's great. If it is so, so I will clear something. I will free some place on the screen, and it is necessary to say that sometimes we don't have to know we don't have to know speed or velocity as vector. Sometimes it is enough speed, I can say velocity. It may be written also. Sometimes absolute value is enough, and in this case we can write that v is the same as absolute value of vector v, and this is the same as vx to the power of 2 plus vy to the power of 2 and plus vz to the power of 2. And how to define this? Of course, we maybe the simplest way to define this is to use a formula above, and we can see that it is equal to absolute value of dr divided by dt. And this is the same as absolute value of dr divided by absolute value of dt. And here we can notice that increase of time is always a positive value. And the absolute value uh, of positive is always equal to this value. So we can remove this modulus without changing of value, and this is the same as dr by dt. And if we look here, we can notice that we can write this as a derivative of path length. So absolute value of velocity or instantaneous speed can be calculated as derivative of path length. Can be calculated as derivative of path length. And I will remove some intermediate formula. And leave just final result. So in this way we defined instantaneous speed or velocity, and this is enough to describe motion with good accuracy. And it is necessary just to say that sometimes it is necessary to in some exercises it is necessary to calculate average path velocity. Uh, it is equal to v in angular brackets, but without line above the letter v. Absence of line means that we have scalar value. And so it may be written as in time t plus at time t plus delta t minus s at time t divided by increase of time delta t, or what is the same as delta s divided by delta t. So it is another type of average velocity. And as you can see from here, average displacement velocity and its absolute value is not enough to average path velocity. So these are different values. So, okay, do you have any more questions about this?
Nope. Nope.
Not okay. Okay, that's great. And what is necessary to say that coordinates may change in time, and of course, velocity may also change in time. Velocity may also change in time, and the derivative of velocity is known as acceleration. So, what is acceleration? Uh, I'll I'll define instantaneous acceleration. Acceleration. Uh, in the same way as it was done for velocity, we can write definition of acceleration only just by substitution of v by a. A vector is acceleration. And this is equal to derivative of velocity. And we can remember that velocity is derivative of radius vector. We can remember this, and if we remember this, we will have first derivative of dr by dt, and first derivative is the same as second derivative. It can be written as in this way. Second derivative of radius vector. Well, this is acceleration. Definition of acceleration is necessary. To learn of the second Newton's law of motion, because this law of motion contains acceleration, so definition of acceleration is necessary. To understanding the second Newton's law of motion. And in the same way as it was done for velocity, we can write coordinates of acceleration, Cartesian coordinates, ax, ay, and az, and plus az multiplied by k. And what does it mean? If we look here, Vx, Vy, and Vz are derivatives of coordinates, and in the same way, Ax is a derivative of coordinate Vx, or not coordinate, component Vx. And this is the same as second derivative of coordinate x. Second derivative of coordinate x. And the same formula may be written for y and z. So in the same way we will get the same way we have that for y and z components we have very similar formula. Very similar formula, but it is necessary to change x with y, and with z. And with z. Okay, do you have any more questions about this?
No. Maybe after the when we see the example, it will be fine.
Mhm. Okay, we will have examples.
Okay.
We will have examples next week on
Mm-hmm.
Thursday, and we will learn them, and we will see how to use this formula.
Can I ask one more question? Where will you upload this video? YouTube or Telegram? Or do we have
Yes,
Classroom?
yes. I will send link on YouTube channel
Okay.
into our Telegram group.
Okay, teacher. Thank you.
So you will be able to watch this, and of course all these things are well known, so they can be found in internet, but it is just necessary. It is just necessary to know what to find here. And I think to pass the exam, it will be enough. It will be enough for you just to visit lessons, and sometimes to make interesting comments about uh, exercises, and to do some homeworks, and it will be enough. It will be enough to get a good grade. To get good grade at the end of the semester. So just to visit lessons, and answer some simple questions. Answer some simple questions during learning exercises, and to do some homeworks. After practical lessons that we will have. First practice we will have next week. Next week on Thursday. Because every 2 weeks we have two lectures and only one practice. I think it is a little. It is not enough. It is not enough to understand physics. But I hope just some things, at least some things, we will get from this. We'll get some of this. So this is acceleration. And what is necessary to say? What is necessary to say? It is necessary to say that this definition of acceleration sometimes is not useful, but it is useful. But sometimes it is not convenient enough, because velocity is a vector. Velocity is a vector, and this means that it may change its absolute value, so its length, and it may also change its direction. So length and direction of vector may change, and sometimes it is necessary. It is necessary to describe separately change of direction of velocity and change of absolute value of velocity. And to describe this separately, let's have a look at a so-called uniform circular motion. Uniform circular motion. So what is this? It is a motion of material point around a circle, with radius r. So I will draw a picture. I'll try to draw a picture. So let's have a look at this some line of circle. Line of circle. On this circle, we have material point that moves along the circle, and length of this line is path length delta s, and the turn of this angle is delta p. Radius of the circle is r. Radius is r. And velocity is always tangent to trajectory. Velocity is always tangent to trajectory. So velocity is here. It is tangent to trajectory. So, and here velocity is here. And if we have uniform motion means that absolute value of velocity doesn't change, but its direction changes with time. Direction changes with time. So in this case we have v, and here we have v plus delta v. And of course, scalar value is the same. So it means that we have absolute value of v is equal to v plus delta v. V plus delta v. But vector values are not the same. So of course, vectors are not the same. It is necessary to take into account this fact that vector values are not the same. So in this case, delta v shows just change in direction, but not to change in value. So uniform circular motion is a good case to define an acceleration as a change of velocity vector in its direction. So let's try to define this change in direction. I will draw again vectors v and v plus delta v, and I will draw this again in this way. I'll move vector v plus delta v to unite its begin with begin of vector v. So we have here vector v. Here we have v plus delta v plus delta v, and according to this picture we can see that vector delta v is here. Vector delta v is here, and in this triangle, these sides are equal. So we have triangle with equal sides according to this. And so we can write perpendicular, and because sides of the triangle A are equal, this perpendicular will be also median. It will be also a median. So it's necessary just to a little bit fix this picture. In this way it will be correct. And what else we can see? We can also see that vector v rotates with radius r, and here we have straight angle. Because velocity is tangent to the circle. So according to this, we can say that this angle is equal to this. So these angles are equal. According to the drawn pictures. And from this we can notice that this angle is equal to delta phi divided by 2. And from this picture we have that delta v is equal to v multiplied by sinus. Oh no, it will be double. Of course, double sinus delta phi divided by 2. Why? Because here we have the right triangle. And from this right triangle we have this delta v is equal to double v multiplied by sinus of delta phi divided by 2. Okay, and let's again consider infinitely small time. Let's consider increase of velocity during the infinitely small time. When time infinitely small, increase of velocity, this dv, will be also infinitely small, and it will be equal to double 2 multiplied by v multiplied by sinus of infinitely small angle divided by 2. Infinitely small angle divided by 2. And here it is necessary to remember calculus again. Remember calculus again. I think in calculus you have learned limit. You have learned limit that can be written as this: x tends to 0, sinus of x divided by x, and this is equal to 1. It is from calculus. It is a limit from calculus, and it means that if we have infinitely small value x, we can write that sinus x is equal to x. But it is necessary to notice that this formula works only in case where x in radians. If we have x in degrees, if we have angle in degrees, this will not work. So in this case, x and phi are in radians. But we can use this here. And it will be 2 multiplied by v multiplied by d phi divided by 2. And this will be v d p. Okay, do you have any more questions about this?
Nope. It's okay.
No, okay. And what else we can say? As we noticed, angle change of angle delta phi tends to 0. But sum of angles in a triangle is always equal to p. It means that when this angle tends to 0, these two angles tends to p divided by 2. So these angles tends to p divided by 2. And it means that vector dv in this case, I will draw this here. It will be directed to the center of the circle. So we have dv is here. dv is directed to the circle because according to this picture, these two angles tend to p divided by 2. And because of this, dv vector is directed to the center of the circle, and so we can define. In this case, it will be useful to define so-called normal vector, and that is directed from material point to the center of the circle, and its length is equal to 1. So absolute value of normal vector is equal to 1. It is sometimes it is used in calculus. Sometimes it is used in analytical geometry. For example, to define orientation of plane in space. To define orientation of plane in space, this normal vector were used in analytical geometry. And with this normal vector, we can rewrite this formula in as a vector, as a vector equation. So change of direction of velocity is equal to v multiplied by n and multiplied by dphi divided by 2, multiplied by dphi divided by 2. Okay, we almost there. We almost get acceleration. We almost get a normal acceleration that shows change in direction of velocity. And what else it is necessary to notice? From this picture, we can also notice that delta S is equal to R multiplied by delta phi, because phi is angle in radians. So from here we have that delta phi is equal to delta S divided by R, divided by radius. And it means that from here we can notice that dv, change of direction of velocity, is equal to absolute value of velocity multiplied by and why did I write this in denominator? It will be just the phi. It will be just the phi without 2 in denominator, because we have this. So it will be v multiplied by n and multiplied by ds divided by r. And this will give us answer. How to define normal velocity. Normal velocity is a part of velocity that shows change of velocity, change of direction of velocity. It is normal velocity. So normal velocity it will be an vector. An vector is equal to v, dv, so first derivative dv by dt, and it is equal to v normal vector n divided by r, and ds by dt, ds divided by dt, and ds divided by dt, it is modulus of velocity according to this formula. We have already studied this, so we can write this as v n divided by r and multiplied by v, according to this formula above, and the final result will be squared v divided by r and it will be multiplied by normal vector n. So this is normal acceleration. So I can write that normal acceleration is equal to squared v divided by r and multiplied by n. Okay, do you have any questions about normal acceleration?
Nope. I will work tonight for this topic.
But I think it is not necessary to work tonight because it is necessary to sleep at night.
Yeah.
It is necessary to sleep at night because if you don't sleep at night, you will not be able to learn anything. So it is necessary to sleep, and as I have already said, it is just necessary to visit lessons, be active, do something, and it will be enough. It will be enough to automatically get a high grade. So everything will be okay. And I will write that this is normal acceleration. Normal acceleration. It is normal acceleration. Normal acceleration. Okay, now I have to remove some intermediate formula from the screen, and just leave this normal acceleration. We need only this now. Okay, and now it is necessary to consider general case. In this case, we have motion along any trajectory, with any velocity. It will be something like this. So in this case, we may also define some vectors that will show directions, vector tau and vector n. Vector tau and vector n. Lengths of these vectors are equal to 1. So absolute value of vector tau is equal to absolute value of vector n, and this is equal to 1. This is equal to 1. And vector tangent vector tau has the same direction as velocity. Has the same direction as velocity. Has the same direction as velocity v. As velocity v. And what is necessary to know that the formula for normal acceleration will be the same, even in this general case. But what about full acceleration? What about this? According to the definition, we can say that a is equal to derivative of velocity by time, and it will be equal to vector sum of change of velocity along vector tau dt plus change of velocity in normal direction. But as it was mentioned above, change of velocity in direction of vector tau is change of its absolute value. So it can be written as first derivative of this multiplied by tau vector and plus the second term. The second term is change of velocity in normal direction. But as it was proven above, this change is equal to normal acceleration. That is written here. So we can write that it is equal to v divided by r multiplied by n. And here we have normal acceleration, and this term is known as tangent acceleration. This term is known as tangent acceleration. So what do we have? We have that this is equal to a tau plus a n. So full acceleration may be represented as a vector sum of tangent and normal acceleration. Tangent acceleration shows change of velocity, change of absolute value of velocity, and normal acceleration shows change of change of the direction of velocity. So I will write this in short way. A tau tangent acceleration is equal to dv dt multiplied by tangent vector, and this is equal to let's remember that v is derivative of path, so it can also be written as second derivative of path with time. Second derivative. Okay, do you have any questions?
Nope.
Not.
Okay.
It is tangent acceleration. It is tangent acceleration. Tangent acceleration. Okay. Well, I will remove some. Intermediate formula. So acceleration may also be defined in this way, and we can unite this. We can unite this formula. We can unite this formula and write them in the same frame. But before doing this, it is necessary to notice that tangent acceleration is directed along tangent vector, and normal acceleration is directed along this vector. It means that we can make picture. We can make picture. So we can show these accelerations on the picture in this way. So we have tangent acceleration here and normal acceleration here. So it will be a tau, and here we have a n. Here we have a n, and their sum will be equal to a. Their sum will be equal to a, the full acceleration. And as you can see, here we have the right angle, because the angle between tangent and normal accelerations is equal to p divided by 2. And here we can use Pythagoras theorem. According to Pythagoras theorem, the absolute value of acceleration is equal to square root of squared tangent acceleration plus squared normal acceleration. So here is a vector formula, and here we have scalar formula. So it is important not to confuse scalar and vector values in order not to make mistakes. It is not good. What's wrong with this frame? Why? Okay, I'll rewrite this frame. Rewrite this frame in this way. Write this frame. So I'll make it red. Okay, that's all about acceleration. That's all about acceleration. And okay, do you have any questions?
So far, so good.
Okay, so I think it is enough. It is enough for today. It is enough for today. We will continue. We will continue this next week, and we will have one more lecture on Wednesday next week, and then on Thursday we will have practice. We will have practice, and we will try to use this theory and understand this deeper. Okay, thank you for your attention.
Thank you, teacher. Have a nice day. Have a nice week.
Okay, have a nice day too.